Here we go. So yeah, Annika, thank you for the kind introduction. And I would like to talk a bit about the PDW technology, PDW spectroscopy, which reads for photon density wave spectroscopy. We are a small company, started in 2013, so good 10 years ago. And we focus on the development and commercialization of this technique. We are based in Potsdam and we are a spin-off from Potsdam University. And in principle, this technology is very good for any turbid liquids. So whatever exhibits significant light scattering, this is the material to analyze by PDW spectroscopy. And it's a probe-based inline fiber optical technique. That means we immerse process probes into the processes and then check on what's going on with the particles, cells, or droplets. And why is that of help in the process analytics business? Well, there are, of course, many materials which exhibit turbidity. We call this turbidity, or we express turbidity by the so-called reduced scattering coefficient, mu s prime. And many materials exhibit really strong turbidity. Imagine milk or cosmetics, polymers, but also fermentation, broth fermentation, cultivation, due to the cells in there, exhibit turbidity. And many take probe-based approaches for measuring turbid processes, that is, turbidity probes, face the issue that they can't really work nicely in high concentrations. So when you measure concentration series of particle systems, you do like a dilution series from higher concentrated states to zero. Turbidity probes may react in a way that towards higher concentrations, they simply saturate with respect to the signal which is deduced. And of course, it's a problem when it's a really flat response, because then you can't discriminate for concentration changes. But also a nonlinear signal response, of course, may pose challenges because you need to do model development and so on and so forth. PDW spectroscopy is a bit different. So we have the same turbidity data as shown here in the mid graph over here, and the response from the PDW spectrometer in blue and red as the reduced scattering coefficient. And this scales linearly over a much larger range. So it's much more suitable for higher concentrations. And there's one further effect which can happen, of course, in turbid systems. It may not just occur light scattering, but also light absorption. So if you think about a just conventional extinction attenuation experiment, what you would measure in such an experiment is the attenuation, so the black curve, which is actually the sum of the two processes. So the sum of the scattering contribution and the sum in blue shown here, the absorption contribution. And with the normal attenuation measurement, you can't discriminate between the two parameters. And this is what visualized here in this array. Scatterer concentration goes up here and absorber concentration goes up there. So there are some samples, like for example, this one here and this one, which optically exactly look the same. They have the same optical impression, but their chemistry, their physics, so their composition and everything is completely different. And PDW spectroscopy is one of the very few techniques which can discriminate between the two processes and separately determine absorption and scattering. So the concept behind PDW spectroscopy is that the results are the reduced scattering coefficient and the absorption coefficient. The absorption coefficient tells something about the color or the chemical composition or the temperature of the material, like this any absorption spectroscopic approach. The scattering somehow tells us something about the particle, droplet, and cell characteristics. And for some industries, particle size is then of relevant. So from the scattering by Mie theory and theory of dependent light scattering, you can get to particle size. This translates to very stable particle sizes measured over high concentration ranges. So this one is here like 60 volume% for polymers. So which means that if we can measure at really high concentration particle sizes correctly, we can probably also do it during process monitoring. Well, for bioprocesses, this is maybe not so relevant here. From what we have done so far is we look in the scattering coefficient to observe process changes during manufacturing. The first example which I want to show, and this is not so relevant for bioprocessing, but I want to show you one effect of the separate determination of absorption and scattering. That's simply the milk fat crystallization in fresh milk. Fresh milk means 3.5% fat, just to take it, you take it into your coffee, for example. So when you take that out of the fridge was maybe at 5 or 6 degrees C, and you heat the milk up. This is the black line here, yeah, temperature of the milk. You heat it up. What happens when you heat the milk from 5 degree to 40 degree? Well, the triglycerides, so the fat starts to melt. Yeah, the triglycerides starts to melt at a given temperature. And this can be observed by PDW spectroscopy. So the squares are the absorption coefficients. And at that measurement wavelength, they scale exactly with temperature because that's the water absorption band, which is measured here. And this relates to was in relation with temperature. And at the same time, but completely different trend is the scattering. So scattering sees some inflection points as function of time, and it goes down and up again during temperature processing. And indeed, when scattering goes down, yeah, that translates to the melting of the milk fat within the fat droplets. Yeah. And what you can also observe is when you cool down the milk again, that the scattering doesn't go up into the original level. Yeah, so there's a hysteresis, and the time here is not sufficient to recrystallize the milk fat completely. So during these cycles, indeed, the same observations are made, and only if you keep it then cold for a longer period, you can observe the recrystallization of the milk fat. And it's just 3.5% fat, yeah, so that's not so much material in milk, but it can be nicely observed by PDW spectroscopy. And as I indicated, we can separate between absorption and scattering during such processing. How does it work? In principle, we use laser diodes as light sources and guide this light through optical fibers into the suspension. So the light, yeah, emits from the fiber tip, and due to scattering and absorption, such a sphere of light is created in the suspension. Imagine really like a sphere of light. Photons are scattered in any directions. And with the second fiber, we collect light back and send it back to a detector. Now, there's one clue about it. The light which is emitted into the suspension is intensity modulated. Yeah, so not wavelength modulation, but intensity modulation. This intensity signal is generated by a so-called network analyzer. And now this network analyzer can very precisely check on how this wave changes from the emission to the detection side. And changes to the wave will occur in the suspension because since the photons interact with the particles which are present, the wave will encounter some changes. So the amplitude of the wave will change and also the phase of the wave will change. And those two parameters, amplitude and phase changes, can be measured by the network analyzer. And with a lot of theory, which we will not look into today, these changes of the photon density wave are related to the absorption coefficient mu A and the reduced scattering coefficient mu S prime. Currently, the spectrometer, so the instrument looks like this. Yeah, that's a box with a small control tablet on top. This is not so fancy. It's just a metal box. On the rear, we have power supply, 24-volt DC power supply, and you have a USB or LAN connection for computer control. We also can work through virtual machines, so that the instrument can be hooked up in a LAN somewhere. And on the front side, there are maybe the more important characteristics, of course, the power button, but also the connection for the fiber optical probe. You can see some images for the fiber optical probes here on the right side. We work with a couple of optical fibers on these probes, process probes. They are currently available in DN19 and DN25. The DN19 probe is the one we typically use for biotech processes because this goes nicely with a compression fitting through an Ingold port into a standard fermenter. Of course, these probes can also be modified by welding on some special flanges if needed. The typical probe length is like 45 centimeters, but this can be modified. So we've also been probes which have been much longer than a meter if we work in larger reactors. It's purely fiber optical, so no electricity, no focusing lenses, no special technical requirements for the probe, which makes it rather cost effective. And the typical length of the conduit, so from the spectrometer to the probe, is like 10 meters. This can be adjusted depending on the needs. For now, mostly 10 meters was more than enough to fulfill the task. All right, let's look into some processes, and I start with an enzymatic process. Milk coagulation, so cheese making, if you like. In cheese making, you take an enzyme, Chimex, for example, add it to the milk, and then some steps are happening. First step is hydrolysis, then comes an aggregation period, and then a gelling process. What we see here is a scattering as function of time for three different fat concentrations, so standard milk from the supermarket in different fat concentrations. And what you see, first of all, is of course the scattering of these three types of milk is very different due to the amount of scatterer. And then when the enzyme is added, you can see an ongoing process. Interestingly, for the milks containing significant fat amount, we have this like peak in the scattering, then scattering goes down and then it goes up again. Now, if one looks into reproducibility of such data, it is found for the 3.5% fat milk. Repeating this three times, the exact same batch, results in absolutely identical initial progress, and then only at a later stage the trends differ. Yeah. And looking into literature and everything, it tells us something that here in the initial period, hydrolysis occurs. And then we have here the aggregation step. And only when the gelling, so the 3D generation of the gel network starts to occur, we see a not reproducible system. Yeah, the gel network is not reproducible. But this can be nicely followed inline. For example, another easy experiment is, of course, playing around with the enzyme concentration. And if you increase the enzyme concentration, you see an influence on the, yeah, so to say, dynamics in the process, so speed of process, if you like. A further example is algae cultivation, photo and photobioreactors. Usually the phototubular photobioreactors are rather having productivity issues in a sense that they have not significant biomass or not significant enough biomass for our technology. But there are some special photobioreactors which can go up to higher cell dry weight. And one example is shown here that has been a cultivation over like 20 days. It was cultivated also with artificial light. And what you can see here as a function of time in black is the PDW data, and in blue and red, the sampling of the process. So for cell dry weight and accumulated cell volume measurement. And it can be nicely observed if you correlate cell dry. So in that sense, we can, even though it's not shown here, can measure like inline biomass directly from the scattering coefficient. And there's some in this process graph, some interesting effects. What you can observe, for example, whenever the nutrient solution was added in a shot-like approach, this is the way they cultured it, we can see that it rather hinders the growth of these cells. So if you look into the slope here of the growth, then after addition of nutrient, it was rather slower than before. So from my understanding, one should work on the idea, on the concept of nutrient dosing here to have a like more optimal growth of biomass in this cultivation. Another example is yeast cultivation here indeed already with a control loop. So that was done in a standard Sartorius 6-liter fermenter. And here the idea was to control the feed of the glucose by the scattering coefficient determined. Again, the scattering relates nicely with the cell dry weight. And if this happens, of course, you have like this specific growth rate because you see how the biomass develops. And if you have the specific growth rate inline in real time, you can set up a controller in a way that this growth rate should be kept constant in a way that the pump speed of the glucose feed is adjusted continuously. Yeah, so pump speed is nonlinear, yeah, to achieve a set point for the growth rate. This, of course, is then observed with, yeah, scattering coefficient. And if this is done and executed and optimized, indeed here there was like 80 grams per liter, which were achieved in this fermentation setup. And this was done through control of the glucose pump by the PDW spectrometer in real time. That also works for E. coli, for example. Here, not with the controlled batch, but just, sorry, with the batch controlled by PDW. That was not the case here. It was just observation of 3 different cultivations, repeating cultivations. And even though they were supposed to be exactly similar or exactly the same, they performed differently without looking into the details here. But there was one very interesting finding. We correlated the scattering coefficient with the absorption coefficient. So that's a correlation plot without time. Yeah, time is gone here. Just using the optical coefficients, and it was interesting to see how the performance of the bad batch B1 in the optical coefficients really showed a decline at certain points. So just by using optics, it was obvious, so to say, that the batch performance, yeah, will fail. For E. coli, there was also work done to compare a bit on different technologies. Yeah, so the upper one is the Muse Prime from PDW spectroscopy. Then that's the density from Hamilton, I think an earlier version, not the current one. And then the offline OD measurement by titrating and manual work. Yeah. And what was found is that PDW spectroscopy works really nicely over this range, which was obtained here for cell dry weight, and also with a completely linear behavior, and with at the end, so to say, looking into the performance over the entire range, with the best prediction error for the biomass. So how precise you can obtain biomass from an observed scattering coefficient. And one last example for bioprocess control by PDW spectroscopy. It's an example which I like a lot. It has been done at the TU Berlin. It's on PHA production in Ralstonia Eutropa. And actually, by accident, there was one effect observed that we have with the 2 coefficients, absorption and scattering, we see 2 different effects in these particles. With the absorption, it is possible to determine the residual cell dry weight, so the cell dry weight without the accumulated PHA. And with the scattering, it's the complete cell dry weight. So that means the difference between the two tells you about the inline PHA content. And this can be observed very nicely in process monitoring. It's, by the way, there are 2 repeating batches monitored here, so exact process control. They did a really, really great job in Berlin. And for example, you see here when nitrogen is added, that the cells start to grow, or continue growing while the scattering goes down. That means the PHA content is consumed as an energy source. Yeah, so they're in a depletion region and they consume their own fat, so to say, to keep on growing in cell dry weight. While for example, in this period here, where oil is applied as a fat source, indeed they accumulate PHA. So it's a way to allow for inline monitoring of PHA content. And I think the best batch which has been obtained so far is that with those 2 coefficients, they actually made 2 different controllers using for the oil and the nitrogen feed, and had like an optimal growth. So achieved like 120 gram per liter batch with nice PHA content, and really got to a nice process control in that way. All right, these were a few examples on the application of PDW spectroscopy for biomass monitoring. Recently, we're also pretty good in protein process monitoring, protein handling, protein precipitation, for example, without being able to show some graphs there. So the fields of application, I think, are currently further developing. I think one of the big assets is the calibration-free method. Yeah, you do not need to calibrate somehow to get the data out. We also do not need method development as you have it typically with NIR and Raman, like background measurement and so on. For sure, for biomass, you still need to relate the scattering with the biomass concentration. So you need to have one translation. It's not an inline biomass measurement, it's inline scattering, which relates nicely linearly to biomass. But it's still not the same type of method development necessary as with these conventional techniques. We measure two parameters at the same time, absorption coefficient, which informs us about color, chemical composition, or temperature, scattering, which tells something about the particle, droplet, or cell characteristics. These are the absolute optical properties of the turbid liquids, so really absolute numbers having a unit. We operate in the wavelength range from like 400 to 1,000 nanometers. We can work in highest concentrations. And with respect to particle sizing, we typically can measure sizes in the range of 50 nanometer to 500 micrometer. Yeah, that's what I wanted to tell today. We do not just work in biotech medicine. We also look into cosmetics, food industry, chemistry, and we have strong relation to the University of Potsdam, where this all came from, let's say. They concentrate a lot on applied and fundamental R&D. We concentrate on commercial R&D and instrument sales. And of course, are always looking also for collaborations with respect to research projects, development activities, and of course, new applications to see what our technology is capable of. That's what I wanted to tell, and I thank you very much for your kind attention.